Hi, my name is Matthew. I'll tell you how to efficiently batch unambiguous interactive proofs. This is joint work with Bonnie, Rohan, and Yael. Public coin interactive proofs are also known as other Merlin games. Merlin, the prover, wants to convince other, the verifier, that some input X is in some language L. Merlin is all-powerful but untrusted, and other is a weak polynomial time machine. In every round, the other does nothing but sampling random strings and sending them over to Merlin. Merlin, on the other hand, feeds the statement and the random coin flipped by other into an honest prover algorithm to produce answer A and send them back to other. This goes on for many rounds until other applies a final efficient checking algorithm V on the statement and the entire transcript, consisting of the random queries by others and answers by Merlin, and decide whether to accept or reject the claim. We want the interactive proof or an IP system to satisfy completeness. If the claim is indeed true, then there exists some honest proving strategy P that convinces the verifier. Soundness says that if the claim is false, then for any unbounded cheating prover, the probability that the verifier accepts is tiny. Such systems can be useful for delegating computation because a weak polynomial time verifier can check the correctness of an expensive computation carried out by an untrusted but powerful cloud, Merlin. In fact, it is known that any polynomial space computation admits such a system, and this is known as the famous IP equals P space theorem. As you may know, P space is an extremely powerful class that contains languages harder than NP. To verify a space as time t computation, the prover algorithm in Shamir's protocol runs in exponential time, and this is inefficient unless S is tiny. We can ask if we can have a dream theorem where the proving is as fast as the computation itself, so such systems are known as doubly efficient, and the prover and the verifier only needs to read the statement. This is actually known to be impossible, but we can relax the goal and ask for this alternative, where the verification runs in slightly more time proportional to the space. Is this dream theorem, coined as Shangri-La, too good to be true? Maybe not. Assuming collision-resistant hash functions, we can build even more powerful systems. However, such systems, known as arguments, have the downside that they are secure only against polynomial time cheating provers. In our work, we study whether Shangri-La theorem is reachable in the setting with unconditional security and against unbounded cheating provers. The first work that studied doubly efficient proofs showed that you can verify the output of a circuit by paying proportional to its depth as opposed to its size, which would be required if you compute the circuit yourself. This is useful for very big circuits that have small depths. For Turing machines, Shamir's protocol has an efficient verifier, but an exponential time prover. In 2016, a breakthrough result showed that you can verify time t computation with an almost time t prover. Here, epsilon is a very small quantity. The downside is that the number of rounds and communication explodes if you actually set epsilon to be too small. In this work, we show a new regime of parameters. To convince you that this regime is interesting, think of epsilon that is much smaller than 1 over logarithmic in n. Then our protocol is much more efficient than the previous regime. This is actually the parameter regime of interest because we want to make t to the epsilon as small as possible, because it affects the verification time. With our new protocol, a polynomial time verifier can now verify up to n to a square root of log n time computation. Similar results were previously only known for t up to n to the log n to the delta for a very small delta. We note that the proving overhead is a fixed polynomial in n that is independent of t, so the system is also doubly efficient, and we are one step closer to Shangri-La. I'll explain a template for constructing doubly efficient system for Turing machine. The formal claim is that the machine moves from an initial state that contains the input x to a final accepting state in exactly t steps. A natural idea is to try divide and conquer or recursion. Suppose we already have an IP system for verifying the shorter computation of length t over k. We can ask the prover to specify all the midpoints of the computation and verify that the length t computation is correct by breaking up into chunks and checking that all subchunks are valid. However, if we have to run the k copies of the IP system, and if you expand this recursion tree out, you'll find that there is not a saving at all in the end. Here comes the ingenuity of the RL16 paper. Non-trivial doubly efficient batching is actually doable, and you don't have to pay for this factor of k in the recursion at all. Now I'll explain how to batch all. In a batch-proof system, we want to accept if and only if all claims are true. Even if a single claim is false, we reject. Trivially, we can just verify the k claims separately. For NP, this amounts to sending the k witnesses in the clear from the prover. For IP, this means running k copies of the protocol, so the cost is multiplied by k. In fact, for general NP relations, we still do not have any non-trivial batching protocol, and it was studied in a previous work. However, for batch UP, we know that really good protocols with a polylogarithmic overhead exist. And here UP is a subclass of NP, where every statement is promised to have at most one witness. Assuming that we can batch IP optimally, let us compute the efficiency of the resulting doubly efficient proof system. Suppose the cost of verifying one subcomputation using a base interactive proof is m, and the protocol has L rounds. We make the Shamila assumption, namely that there exists an optimal batch verification protocol for verifying k instances of pi0 at the cost of roughly one protocol and an additive overhead polylogarithmic in k. For the base case of the recursion, the verification of one step of transition of a Turing machine is carried out by the author himself after Merlin specifies the two tapes with OS communication, so the cost of verifying this is OS. In the recursive step, Merlin sends all the midpoints using a times s bits. Note that we set the batch size k to be n here. Then Merlin and other runs the Shamila batching protocol, so the resulting cost of verifying time t computation is exactly the cost of verifying one time t over n computation plus polylogarithmic in n, and if you carry out this recursion carefully, it turns out to be log t times polylog n. This is too good to be true, and there are two critical differences from what we currently know. First, similar to the fact that we can only batch UP and not general NP, we only know how to batch interactive proofs that are unambiguous, which I'll define soon. Fortunately, this is enough for delegating deterministic Turing machine computations. Second, our batch UIP protocol has cost m times L times polylogarithmic in k, which is multiplicative instead of additive. Recall that L in this expression is the number of rounds in the base protocol. This leads to a final cost dependency that is the polynomial in t, but not all the way to logarithmic in t in the efficiency of the verifier. Finally, we comment that the original RL16 paper constructed a batch UIP protocol that has a larger overhead dependency on L, and this is why we are able to achieve a better delegation scheme using the same framework. Now I'll define unambiguous IPs as promised. It's very similar to the standard IP setting, in that we required completeness that says there exists an honest convincing prover strategy if and only if X is in L. And for false statements, we assume the honest prover always sends some dummy string, so that we can make the behavior of the honest prover well defined even in this setting. And we also require an ambiguity that says there exists effectively one unique answer that the prover must send in every round otherwise it wouldn't be convincing in the end. Let me summarize what we know for batch proofs. For NP, we know how to batch them extremely efficiently, but with an exponential time prover. This is an easy consequence of the IP equals PC's protocol of Shamir. For UP, the subclass of NP statements with at most one witness, we can batch them quite efficiently with a multiplicative overhead that is polylog k. The prover is efficient if they are given access to witnesses. For batch UIP, the RL16 result batches them at a multiplicative overhead of k to the epsilon. However, the dependency on L is quite bad, and it simply implies that they cannot set epsilon to be small to make them polylog k. In contrast, our result shows that you can get polylog k, and the dependency on L is a single factor of L. Although, all that being said, it's still very far from Shamir with a single overhead of additive in polylog k. Finally, let me give you a flavor of how our main batch UIP theorem is proven. Step 1 is essentially the same as in the original RL16 protocol. First, we run the KUIP protocols implicitly. By implicit, I mean none of the prover's answers are actually sent to the verifier. In the end, other creates a joint constraint C over the K instances. Most importantly, the cost of step 1 for the verifier is roughly the cost of one protocol because none of the answers are actually sent. Otherwise, there would be a K overhead and we are back to square one. This constraint is constructed using error correcting code and enforces that a cheating prover must lie on many instances if it ever not lies. The second step runs the GKL doubly efficient protocol in holographic mode. Holographic mode is a fancy term to mean the verifier does not explicitly read the input to the circuit that is being checked by the GKL protocol. The circuit being checked by GKL verifies that all the prover's answers in the KUIP protocols, if the prover had sent it in step 1, which is not actually the case, those answers would be accepted by the basic UIP verifier, in addition to satisfying the constraint created in step 1. The GKL protocol outputs a low-degree extension, or Reed-Muller code constraint that A would satisfy if A satisfies the GKL claim. You may wonder why we want to move to a Reed-Muller code constraint. This is because Reed-Muller code, which is based on low-degree multivariate polynomials, have a recursive structure that allows us to perform certain code folding procedure. This code folding magically reduces the number of active UIP instances down to k over 2 if you carefully perform the folding, which requires considering a metric slightly different from Hamming distance in the code space in our UIP scenario. However, this folding procedure is secure only if there are sufficiently many lying instances that are inconsistent with the GKL claim in the batch. Fortunately, we have already established that the prover has to lie on many instances in step 1. Since we are left with k over 2 instances, and at least one of them is false if the original batch is false, we can go back to step 1 and continue halving the batch size until we are left with log k many instances, and the number of halving is also log k. That's why we can perform in brute force in the end, and the overall overhead is a multiplicative factor on top of one protocol. I'll tell you about unambiguous IPs and how to batch them in the rest of the talk. Let me set up some notation. Given others coin denoted as Q1 up to QL, let Aij to be the prover's jth answer to the ith instance, and we organize them in a matrix A, where the rows corresponds to the instances and the columns corresponds to the rounds. A simple idea to try to catch a cheating prover is to just do subsampling. And if you pick Q out of the KIPs and then run them explicitly, the probability that you catch a cheating statement when there are D cheating statements is this expression. And this doesn't really give us substantial saving unless the fraction of false statements is constant. We really want the prover to be lying on many instances even though there is one false claim in the first place. How do we do that? We run the protocol implicitly, where in each round, instead of asking Merlin to send the explicit answers, we ask for a checksum of the k answers instead. So instead of k bits being sent, there's only one bit that is sent. For simplicity, we are assuming one bit per round here. This is a pictorial diagram showing what Merlin is doing. And if there's some false claim, Merlin must be lying on some row, otherwise it will be rejected if it follows the honest strategy. However, because of the error correction of the checksum, to be consistent with the checksum that the Merlin sent previously, it must also be lying on another row. And if we use a better error correction code, we can enforce other Merlin is lying on at least d rows. You don't need to know the exact GKR protocol except the following interface. First, there is an explicit input that's a succinct description of the circuit that the verified knows, as well as a holographic input that the verified doesn't touch at all in the protocol. The circuit checks the following. First, every row in the matrix is accepted by the base UIP verifier, as well as that every column in A XOR to the correct checksum that were communicated in the last step. Finally, the GKR protocol outputs the Reed-Muller constraint, and A would satisfy that constraint if and only if it satisfies the circuit. The number of bits exchanged in this phase by the W efficiency of GKR is proportional to the depth of the circuit, which is roughly log k, maybe plus the depth of the verifier as well. The R protocol subsamples the rows or the active instances in the matrix. It takes in the Reed-Muller claim about the matrix and output a subset of rows and a smaller claim over those subset of rows. So pictorially, those are the errors and the matrix and the constraint. The interactive coding, code folding R protocol, folds it into a smaller matrix and a smaller constraint, and we modify the protocol such that it always folds the error along the columns instead of arbitrarily. The number of bits exchanged is polylogarithmic in k, and the number of rows is halved, so we can just recurse. And as long as there are sufficiently many rows containing errors, there will be at least one row containing error as well in the end. Seems like we are good to move on to a new step 1. Unfortunately, the UIP becomes secure as of now because the entire sequence of Q is already reviewed to Merlin, and the UIP is only secure if other generates the random coin on the fly. We cannot reuse those queues for this reason in the next step 1. But changing the queues will change the corresponding A, and if we recall, the R step produced a new constraint that would not be satisfied by the row specified by A. If we change A, then it doesn't make sense because this little constraint is not talking about the same A anymore. What is the solution? It's actually very simple. We can run L copies of the UIP implicitly, and recall L is the number of rounds, and in each one of these copy, Merlin other challenges Merlin to continue a prefix of the original random coin, but with a fresh suffix of new random coins. And this is exactly why in our overall batch UIP, there's an overhead of L instead of without L. To conclude with some concrete open problems, I'm obsessed with this batch MP questions studied in this paper. They showed a negative result stating that if you get sufficiently non-trivial upper bound, then there is some complexity theoretic consequences. However, it would be nice to either show a stronger negative result or show slightly non-trivial upper bound. The second question is whether we can improve our batch UIP dependency further to remove the factor of L. If we can do that, we can verify up to time n to the square root n to the log n without a square root. More generally, I wonder if there are new routes towards Shamila. Having to send a k-midpoint states really mean the batch size should be polynomial, and it's counterintuitive because most people would have expected the batch size to be extremely big. Do we have new applications of batch UIP and batching proofs in general other than delegating computation? And last but not least, what is a better name of Shamila? Thank you for listening.